This is Math 139, and we're in section 4.12, part B. The next application of radicals that we're going to look at is the Pythagorean Theorem. The Pythagorean Theorem, you've probably seen this one before in math classes, but it refers to the lengths of the sides of a right triangle. It does have to be a right triangle, one with a 90-degree angle. A and B are the shorter sides, called the legs. C represents the length of the longest side, called the hypotenuse. And then the theorem tells us that a squared plus b squared equals c squared. If I were to sketch a picture that illustrates that, I'm going to draw my right triangle here. Right triangle, that little square in the corner shows the 90-degree angle or the right angle. A and B, the shorter sides, are the legs, and C, the long side, or the hypotenuse. All right, let's do a couple of problems using that theorem. Here we have the two shorter sides given, so A is 8 and B is 5 square root 5, and our C is unknown. So if I plug those into my Pythagorean theorem, I would have 8 squared plus 5 square root 5 squared equals my unknown, c squared. 8 squared is 64. And although certainly a calculator will square that for you, let me just remind you that because these are multiplied, you can just square both factors. So 5 squared would be 25. Multiplied by squaring the square root would give me 5. Makes that a 125. If you are not as comfortable doing that by hand, again, you can do it on your calculator. If I just take 5 times the square root of 5 and square it, there it is. It gives me that 125 as well. All right, adding these together is going to give me 189. And so to solve for C, I would need to take the square root of both sides. And let's see here. I don't think that comes out evenly, but it looks to me like the perfect square 9 goes into there. That would be 9 times 21. Or 3 times the square root of 21 would be the simplest radical form for the value of C. One thing I will notice, I put a square root in this equation, and I didn't bother with the plus or minus. Remember, usually when you take a square root inside of an equation, you have to think about both the possibility of a positive square root and a negative square root. But in this case, I knew C was the length of a side. So I already knew I wanted the positive square root, and I didn't bother indicating the possibility of the negative. All right, let's try another one. In this next one of the short sides is unknown. I'll say that's A. B is 9, and C is 11. And so again, I'm just going to plug those values into my Pythagorean theorem. So A squared, A is unknown, plus 9 squared equals 11 squared. C, 9 squared is 81, and 11 squared is 121. So to solve for A, I'll subtract the 81. It's going to give me 40. And once again, to get A, I'll need to take the square root on both sides. Because A is the length of that leg, I'll only worry about the positive square root. To simplify my radical, 40 would be 4 times 10. So the simplified form would be 2 times the square root of 10. All right, let's look at a couple more. In example 3, I have one leg with length 4. The other leg is not known, but they give me a value for it. They're going to call it x. And then the hypotenuse is completely unknown. So I'm going to consider the 4 and the x as givens and assume that they want me to solve for the hypotenuse, c. Now when I do this x is going to have to be part of my answer. There's no way to get rid of it. But I will solve my final result for c, the side that was not labeled. So Pythagorean theorem, a squared plus b squared equals c squared, would be 4 squared plus x squared equals c squared, or 16 plus x squared equals c squared. As I said, we want to solve for the c, so we'll go ahead and take the square root on both sides. Positive square root only, since this is the length of the hypotenuse. And this is where you want to remind yourself some of those tempting things that you really can't do, right? It looks really tempting to just make that a 4 plus x, but it's not true. You cannot separate a sum or a difference and take the square roots separately. So this is as good as it gets. It's common to write the variable term first, so I might just rewrite this as the square root of x squared plus 16, but I cannot simplify that any further than that. In part D, we once again have some variables in the description. So 3a and 4a are the lengths of the legs, and once again the hypotenuse c is unknown. So let's see, you know what? I'm going to write my Pythagorean theorem with capital letters this time simply because I've got a as part of the labels here. Call that capital A, and I'll call this capital B. So A is 3a, and I have to square that whole thing, so parentheses there, plus B, which is, again in parentheses, 4a, square that, equals c squared. This is a product, so I can apply the square to both factors, right? That would be 3 squared is 9 times a squared. And the same thing here, applying that square to both factors. 16a squared equals c squared. And those are like terms, so I can add them up. 25a squared equals c squared. I'd like to solve for c, so I'll take the square root on both sides. Positive square root is fine since it's a length. And now this time, I can simplify, right? I don't have a sum like I did here. I have a product, and it's okay to separate and take the square root of the two factors separately. That's just 5a. Okay, so kind of an important distinction between those. You can't break apart a sum or a difference under a radical, but you can do it when you have factors. All right, that brings us to the end of section B. I think we're going to go ahead and do section C here as well. That was kind of a fast little piece. The last application for radicals that we're going to look at is the distance formula. The distance, by which we mean the straight line distance, between 2 points, x1, y1, and x2, y2, is given by this distance formula. The difference, x2 minus x1 squared, plus the difference, y2 minus y1 squared, and then you take the square root of the whole thing. Okay? So literally, if you have your points, x1, y1, and x2, y2, that distance formula is the length of that line, the distance between the 2 points. All right, in our first example, we want the distance between the points 2, 1 and 6, 4. It says to go ahead and graph them, and then it asks us another question, but let's go ahead and just find the distance first, and then we'll worry about the rest of it. So, based on the givens, I have an x1 and a y1, an x2 and a y2, and I'm just going to plug right into that formula. First I need x2 minus x1, so 6 minus 2. Square that. And then y2 minus y1 would be 4 minus 1. Square that. And that's all under the radical. All right, that would be the square root of 4 squared plus 3 squared. And again, remember, this is a sum. I can't just take the square root separately. I'm going to work it out instead. That's 16 plus 9 under that radical. Square root of 25, or 5. So those 2 points are 5 units apart. Now let's go ahead and actually graph the points. Then we can think about the question that they asked. 2, 1, and 6, 4. And what we've just determined is the length of this line is 5. The question then says, do you see why the distance formula works? It's really just another statement of what famous theorem? I'm going to put these in as dotted lines. But notice, I could think of that line that I just drew, that distance, as the hypotenuse of a right triangle. This side is 1, 2, 3 units. This side is 1, 2, 3, 4 units. And a squared plus b squared equals c squared. Right? The 3 was the difference in the y's. The 4 was the difference in the x's. So all of those are really just another way of saying the Pythagorean theorem. This is just a form of the Pythagorean theorem. All right, let's look at one last example. Number 2, we're asked to show that the triangle ABC is a right triangle, given the values of A, B, and C, the points. So I'm going to go ahead and I'm going to plot them first. A is negative 2, 1. B is 2, 3. And C is 3, 1. So there's the triangle that we're talking about. It seems fairly clear to me that if it's a right triangle, this angle right here at point B would have to be the right angle. None of the others look like they would even be close. Now, just by looking at it, though, I shouldn't conclude that that's a right angle. I mean, is it 90 degrees or, is it 88 degrees? I can't tell that just by looking. So I'd like a mathematical proof that this really is a right angle. The easiest way, I believe, for us to do that is going to be to find the lengths of all 3 sides. And if we can show that they satisfy the Pythagorean theorem, then we must have a right triangle. So let's go ahead, and I'm going to use lowercase letters for these. I'll call these sides A, B, and C, anticipating that we're hoping this is going to turn out to be the hypotenuse. And we'll calculate the length of each of those sides. So for side little a is the distance from B to C. So B is 2, 3, and C is 3, 1. So I'm going to calculate using my distance formula. The square root of x2 minus x1 is 3 minus 2 squared plus y2 minus y1, 1 minus 3 squared. So I've got the square root of 1 squared plus negative 2 squared. That'd be 1 plus 4, or the square root of 5 for A. I'm going to do that same exact thing for B and C. So we're going to run through that process a couple more times. B is the distance from A to B. And the point A was negative 2, 1, to the point B, which was 2, 3. So I'll use my distance formula again. The square root of x2 minus x1, 2 minus negative 2 squared, plus 3 minus 1 squared, see, 2 plus 2, that'd be 4 squared, plus 2 squared. 16 plus 4 is 20. And I'm actually just going to leave it like that. Well, I don't know. You know what? We'll go ahead and simplify it. Square root of 20 is the square root of 4 times the square root of 5, or 2 times the square root of 5. All right, one more. C. Now C, I might cheat a little bit. You could use the distance formula again if you wanted to, but notice C just happens to be just nice horizontal line. So I think we'll go ahead and just say, let's just count. 1, 2, 3, 4, 5. C is 5. We just counted. All right, our question then becomes, is the Pythagorean theorem true? Right? I didn't label these, but this was A, and that was B. So we're now going to check. Is it true that A squared plus B squared equals C squared? Well, let's see here. A was the square root of 5. B was 2 times the square root of 5. And C is 5. When I square the square root, I'll just get a 5 here. Because they are multiplied, I can apply the square to both factors. So 2 squared would be 4, multiplied by squaring the square root gives me 5. And on the right-hand side, 5 squared is 25. 20 plus 5 is indeed 25. And so it looks like the Pythagorean theorem did work. We know the Pythagorean theorem only works for right triangles. So since the Pythagorean theorem worked, I'm going to be able to conclude that this is indeed a right triangle. All right, that brings us to the end of section 4.12.